Here's your homework. Leo? Leo? Yeah. Josie? Josie? Rick? Ben? And Jake. Anybody have any questions on anything that was on the test? On the last page, it says some scanners store a scanned pixel as a 32-bit number. How many different colors are such scanners capable of representing? And that's just a number of 32-bit combinations that there are, and there's two possibilities for each bit, so it's just 2 to the 32nd is the answer that I was looking for there. And then on the other two, the next thing, the only tricky one about that was that you needed 4 digits and a sign, which is 5
values that you need to represent. But we need to represent them in a number of bytes. Put the leading 0 on the wrong end, maybe, or something. But you know, in general, the scores are pretty good. There was 3 A's, 3 B's, a C, and a D, but one of the B's was an 89, so that's almost an A, and the D was a 69, that's almost a C, so. So that's not too bad. I'm going to at least try to do Zoom recordings of our class sessions, and we'll see how it goes. So that's what this is for today. Yeah. You know, if you can't decide what to watch on Netflix, you can always pull this up. So let's go to our homepage. Is the homepage coming up okay for you guys? I was having all kinds of problems getting my web pages to show up this morning, but looks like you guys are okay. Okay. Click on the review of gates and digital functions. There's a link there. So our basic building blocks that we're going to be using are going to be the and, the or, the not, the NAND, which is not and the NOR, which is not or. So you got several ways to represent these. You can use the circuit symbol, which is in the second column. You can write it algebraically, which is what's in the third column. You can create a truth table, which is obviously a whole lot more work, and that's what's in the last column. So those are the building blocks we're going to be using. Exclusive OR was another one that we mentioned, but I don't think we have any use for that on any of the homework assignments. So these are the 5 basics that we'll be doing. We're going to be building a number of circuits here in the next couple of days, and those are the things that we'll be using to build them. Okay. So what we tried to figure out the other day was if we take A and B, this is what we did, right? We took A and B and the complement, and we want to know if that was equal to the same as taking the complements and ANDing them together. And we built a circuit that did this, we built a circuit that did this, and we found out that you don't get the same outputs when that happens. Okay. So these 2 circuits are not equivalent. What we're going to be doing is we're going to be looking at some ways to tell if circuits are equivalent or some ways to simplify circuits. If you can simplify a circuit, it takes fewer electronic components. It will be cheaper to build. It won't take up as much space on the chip and so on. So you want to have circuits that are as simple as you can possibly make them. And so we're going to be looking at some ways to simplify circuits here today. And let me see. So the other day we looked at 2 inputs. So we had like A and B. I had this little chart up here. Actually, it wasn't all that little. Where we've got all possibilities of 0s and 1s for A and B. We've got 2 inputs here, and there's 2 possibilities for each one. So the number of inputs and the number of possibilities for each one will tell you how many different combinations you're going to have. So there's 4 possible combinations of 2 inputs. And then, I don't know if you paid much attention or not, but I numbered these F0 all the way through F15. And F0 looked like this. And F1 looked like this. And F15 looked like this. And if you simply turn your head 90 degrees and look at this as a 4-bit number, that's the number 0, that's the number 1. The next one would be the number 2, which looks like that. The next one would be the number 3, and so on, okay? So those are all the possible, there's 16 possible functions that you could have of 2 inputs. And, you know, some of them we just threw out, some of them we kept. Now, what if you have 3 inputs? What if you have A, B, and C? If you have A, B, and C for inputs, then we've got 2 to the 3rd, and I need 4 more rows here. And then I'm going to count from 0. Let's just count in binary here. That's the number 0. That's the number 1. That's the number 2. That's the number 3. The number 4. The number 5. The number 6. And the number 7. Okay? So if you get 3 inputs, 2 to the 3rd. You got 4 inputs, 2 to the 4th. Now, how many different functions are there of 3 inputs? How many of these columns will I have? It's not too hard to figure out. It's 2 to some power. Actually, that's the answer to almost everything in this class, 2 to some power. What's the power? What? No. We had more than that with just 2 inputs. We had 16 with 2 inputs. It's going to be more than, so I'm asking, how many columns will there be? It's going to be a lot more than 16. The question is how many? Okay, turn your head sideways, and that's the first number, right? And I just keep counting all the way until I get all the way over here, and I get, what number is that? You guys aren't dreaming in binary yet, are you? Did you know what it is? It's 2 to the 8th. And how do you get 2 to the 8th? There's 8 rows, right? Yeah. So if we want all possible combinations of 8 bits, it's going to be 2 to the 8th. This is the number 0. And if you went and did your place value thing over here, it's 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. And if you add all those numbers up, you get 255. So if we're going from 0 to 255, there's 256 possibilities. Okay. I'm going to add in a 4th input, except I'm going to make my life a little bit easier. Ah, shoot. No, I'm not. I'm not going to write them all down. If I have a 4th input, I would have from 0, 0, 0, 0 for the inputs all the way up to 1, 1, 1, 1 for the inputs down here at the bottom. So that is from 0 to 15. That means there's 16 possible combinations of inputs if you've got 4 input variables, okay? So we got 16 rows. So how many functions are there? 2 to the 16th. What's 2 to the 16th? Quick. I want you to remember this. I'm going to show you a quick way. It'll come in handy for at least for the rest of the semester. It might even come in handy after that. We did this the other day. 2 to the 10th is equal to 1,024, correct? But we usually call that 1K, okay? In the metric system, 1K means 1,000. In base 2, though, 1K means 2 to the 10th. So it's actually 1,024. So 2 to the 10th times 2 to the 10th is 1 million. And 2 to the 10th times 2 to the 10th times 2 to the 10th is 1 billion. Okay? So if the number is bigger than, if the exponent is bigger than 10, then all you do is you start taking tens out of it until you've got a one-digit number left. So if the number is 2 to the 16th, you look at that is that's going to be 2 to the 10th plus 2 to the 6th, okay? Well, this is 1K, and 2 to the 6th is 64. So it's going to be 64K. So that way you never have to memorize any powers of 2 that are bigger than 1024. Okay. So if I have 16 rows, 64,000 possible functions, and I've only got 4 variables over here for inputs. What if I had a 5th variable? Then how many rows do I have? I've got 2 to the 5th rows, and 2 to the 5th is 32. So I've got 32 zeros here, and I go all the way to the end of my chart over here, and I got 32 ones, okay? So how many functions are there with just 5 inputs is all, 5 inputs. 2 to the 32nd different possible functions of only 5 inputs, okay? And that is 2 to the 10th times 2 to the 10th times 2 to the 10th equals 1 billion times 2 to the 2nd, which is 4. So it's 4 billion different functions if you've got 5 inputs, okay? So if you're thinking about, building circuits from basic building blocks, 5 inputs is almost nothing. It's almost nothing. You have, 2 billion little containers on the shelf there, each one holding a different function for 5 inputs. Okay. What you're going to do instead is you're going to build. If you have more than 2 inputs, we just did 2 inputs last Wednesday, but if you get more than 2 inputs, then you can have, we can build them from our basic AND gates and OR gates and NOT gates, okay? Everything can be built from basically those 3 things. So that's what we're going to do instead. So we're just going to use ANDs and ORs and NOTs. And the truth table for AND, if you have 2 inputs and I AND them together, I get 0. That's a 0. Okay. So the AND function means both. And when we're talking about binary digital functions, what we're always concerned about is when you get 1 for an answer, not when you get 0 for an answer, okay? So this means if both of the inputs are 1, then I will get 1 for an output. And in general, 0 is considered to be false, equivalent to false in a lot of this stuff, and 1 is basically equivalent to true, okay? So if you think about it that way, if one thing is false and another thing is false, then the whole thing is false. And if I've got 2 things here and I want to know if they're both true, and means both, if one of them is false and one of them is true, they're not both true, so I'm going to get false for result. If one is true and the other is false, they're not both true, so I'm going to get false for result. If they're both true and I've got an AND, that means if both of them are true, I want to get true for an answer. So that's what my truth table looks like. Okay. What if I have 3 inputs? And I AND 3 inputs together. Well, obviously AND doesn't mean both anymore, but what does it mean? It means all. Okay. So the only place where I'm going to get a 1 for an answer here is if all 3 of the inputs are 1, okay? If I've got 4 inputs, instead of 8 rows here, I'll have 16 rows here. The only one that's going to be true is going to be the bottom one. All the other 15 are going to be false because all of them have to be true in order to get 1 for an output. Now, what if I've got OR, okay? So let's just change this to OR. OR means one or the other, or both. So if this is false and this is false, then obviously the whole thing is false. But if I want to know if either one of these is true, well, yeah, this one is true, so that's going to be true. This one is true, so the result is going to be true when I OR them together. And obviously, if both of them are true, then the result's going to be true when I OR them together. So with an OR function, any place you've got a 1, you're going to get a 1 for a result. Any place you've got true, you're going to get true for a result. And with OR, the only place where you get 0 is if you've got all zeros. So if I had 3 inputs here and I wanted to change this to an OR function, this is going to be the only place where it's 0. Every place else, as long as there's a 1 in there somewhere, they're all going to be true. Okay? If I got 4 inputs and I OR them together, they're going to be true every single time except in the case where all 4 of the inputs are 0. Okay? So OR means any. If you're talking about more than 1 here, it means any, and means all. So if all the inputs are true, the output is true, and otherwise it's false. And with an OR, if any of them are true, the output is true, otherwise it's false. Okay. And the other basic building block is the not. And all the not does is it just takes, you don't have more than one input with a not. You only have one input with a not. So its truth table is very simple. If the input is 0, it converts it into a 1. If it's a 1, it converts it into a 0. So it just takes it and flips it around the other way. Okay. You should have Logisim on your desktop or someplace handy. That logic gate simulator from the other day. Open that up. Now, what we're going to be dealing with for the next few days is we're going to be dealing with digital functions. And they kind of use the mathematics notation for a lot of this stuff. So they will say a function of A, B, and C. So that's just exactly stolen from math. And if I say the function of ABC is A, B, C, okay, you don't put anything in between them. That's assumed to be an and. It's also possible, but you don't see this very often, it's also possible to put a raised dot in between, and that also means and, but usually they just skip that. So this means when I'm defining a digital function here, so this is my digital function. What you define is you define the circumstances under which the function is 1. That's all you care about is if it's a 1. You don't care about when it's a 0. So if I define my digital function to be this, then I'm saying that the function is only going to be 1 when, how do I get a 1 out of this? If I'm adding them together, the only way I can get a 1 out of it is if A is 1 and B is 1 and C is 1. Okay? So if I build myself some kind of a function here, it's got inputs of A, B, and C. The output here is only going to light up if this is 1 and this is 1 and this is 1. Otherwise, the output is going to be 0. Okay. How about if I say my function of A, B, and C is A complement B, C complement. What's that mean? That means if I AND these 3 things together, I'm going to get 1 for an output. Okay? Well, if I'm inverting this and I want it to be a 1, then it better start off as a 0. I'm just leaving this the way it is. I want that to stay a 1. And if I'm going to invert that, I want to start off as 0. So what I'm saying here is that this function will have an output of 1 when A is 0, B is 1, and C is 0. Okay, let's build this one. Okay, get yourself an AND gate and drop it on the screen. And when it's selected, go down to the bottom left. You've got some properties down there. And one of the properties is inputs, and by default, that's always 5. And we want to change that to 3. So change it to a 3. You don't drag these things out on the breadboard. What you do is you click on it, and then you click on it on the breadboard again. Okay. Now let's draw an output line. Just drag a line from that. And the other day, I think I used one of those green ones up on top, but we're going to use there's a red one as well. And if you go look at input, output, there should be a little red ball there that's labeled LED. Finding that? In the input, output folder, there should be a little red ball labeled LED. And I want you to drag that, and the connector's on the left side, so just get the end of it. Get the connector right on the end of that line. Input, output, right there. Click on the LED, drop it over there. You can't drag and drop. You have to click and then click. Okay, everybody's good? Get 3 inputs on your gate. Okay. We're going to need 3 inputs over here. So that's the little, there's 2 green ones up there. It's the one on the left. So there's a little green square. Drag it, or not drag it, but drop one right here, drop one right here, and drop one here. And actually, we don't need to connect these yet because we got to put some inverters in here as well. Now, select this one. Actually, before we do this, take your mouse and just drag it so you select all 3 of those inputs. You should get a box around all 3 of them. And over on the bottom in the properties group, there should be a font option. And it's called label font. Yeah. Label font, and click on it. And right now it says 12. Let's make that about twice as big. Let's make it 24. Properties on the left. You see the bottom property, bottom left. Right there. It says label font. And you want the label font for those. Okay, you picked the wrong ones. It's got to be the squares, not the circles. Okay, so just drag your mouse over all 3 of those and hit delete. Yeah, let's not do that during class. So make the font size 24, and then there is, I think it's called label, right? In the properties down at the bottom. So put an A next to this one, put a B next to this one, and put a C next to this one. I'm in the wrong place. A, B, C. So we got our inputs labeled, and our function says this has to be inverted before it gets to the gate. So get an inverter and put it right here in front of the top input. So you should have 3 little blue dots there representing your input connections for the AND gate. A needs to be inverted. B does not, so just drag B right over. C needs to be inverted, so you're going to have to put another inverter down here. And that's what it should look like. We got some red lines there. I think, whoops, pull that out of there. It looks like you got your red line going through it somehow, and I think that might be what the problem is. So we might just have to delete that, and let's go back and try dropping that in there again. Actually, you know what? I'm going to drag this over to the right a little bit, drag this over to the right a little bit, and I'm going to get rid of that, and I'm going to shorten that up a little so I got room. Okay, and then drag that. See, now it's green. If it's green, you're good. If it's red, something's wrong. So if anything shows up red, you just need to fix it. Okay, so grab yourself another inverter and drop it in there. Yeah, why is that red? It might be, I'm not sure what the deal is with that right there. Great. I get rid of all of it. Let's click there. Let's click there Now you're good. So I think it's that little line there, but I don't know. It's tricky when you get little stuff like that to try to get rid of it. And sometimes you can't select it. So just put another one in. So now you should have, all of your lines should be green. Get a red line or a blue line, something is wrong. So I've got a digital function here. The function is A complement B C complement. That means the only time I'm getting an output of 1 is if my input is 0, 1, 0, okay? Now, go up in the upper left-hand corner and turn the circuit on by clicking on your hand. And then I want you to start off with, 0, 0, 0 here, and you should get 0 for an output. And when you're testing these, what you need to do is if you got 3 inputs, you need to count through all 8 possible combinations. You got to go 0, 1, 2, 3, all the way up to 7. And the only place you should get 1 for an output here is when you get to 1, 0, 1. I'm sorry, not 1, 0, 1. I got it backwards. 0, 1, 0, okay, which is the number 2. So you should be able to go through all 8 of those input combinations. You should get 0 every single time, except when you got 0, 1, 0 as your inputs. Did you test all of them? Okay. Did you test all of them? You tested all of them? Okay, just got to go to the hand there to turn it on. Did yours work? All 8 possibilities, Tamus, all 8 of them? All 8 of them? Josie, all 8? Leo, all 8 of them? Okay. So all we're doing here is we're saying this is where the input is going to be 1. When A, if A is complemented, and we take B as it is, take C and we complement it, we get 1 for an output. If this is true and this is true, then this has to be a 0 and this has to be a 0. So basically, any place where there's a complement there, it means 0. Any place where there's not a complement there, it means 1. Okay, so let's try this. Let's try one that's a little more interesting. You can just delete that circuit, and let's start with some inputs up here. So put 3 of those over there. And so it's going to be a function of 3 variables. And then drag the mouse over all 3 of them. We're going to change some properties for all 3 of them at the same time. And the first property we're going to change is we want them facing south. That'll put the connector on the bottom for us, okay? Drag your mouse over all of them, select them all at the same time. Oh, it's good. Did you get the first one? Okay, okay. Drag the mouse around them again, though, because the other thing we're going to do is there's an option over there for, actually, I'm not sure about this. Is there an option for the label position? And that's north, south, east, or west? Okay, we want north. So with all 3 of them selected, so you don't have to do this 3 times, choose label, position, and choose north, and that'll give us labels up here, up. We're gonna have our lines coming out on the bottom. And the other thing we wanna do is we wanna make the font a little bigger. 12 is kind of small. So with all 3 of them selected, go down and change the label font to like 24. I think that's readable, much more readable without being too big. And then you can deselect them and just select the first one and put a label on it of A. Select the second one, put a label on it of B. And select the third one and put a label of C on the third one. Okay. So I get 3 inputs, A, B, and C. And we're going to drag this one down quite a ways. We're going to drag this one down quite a ways. And we're going to drag this one down quite a ways. And I'm going to tell you that the digital function we want is A complement BC or A B complement C or A B C complement. So these are three things that are going to be ANDed together. I'm saying I want 1 when A is 0 and B is 1 and C is 1. So 0, 1, 1. Here I'm saying I want a 1 when A is 1 and B is 0 and C is 1. If all three of those are true, then I get a 1 for the output. And on this one, I want to AND A and B and C complement together to get a 1. So I need to have a 1 and a 1, and the 0 needs to be inverted on the C, so I get a 1, okay? So here's an AND gate with 3 inputs, here's an AND gate with 3 inputs, here's an AND gate with 3 inputs, and then I'm going to run all 3 of them through an OR gate at the end, okay? So let's put an AND gate right here, let's put another one right here, and let's put another one right here. Then select all of them and set the number of inputs to 3. You have to make those a little bit longer too. Okay. Now every place where there's a complement here, we need an inverter. So we need an inverter in front of A. And we're going to do this to make our lives easier. We're always going to put A as the top one, and B as the second one, and C as the third one on each one of these AND gates. Otherwise, it's really hard to read. So we want an inverter for A here. We want an inverter for B on the middle one, and we want an inverter for C on the bottom one. And then just take this one is always, the top one's always going to go to A over here. If you see a little dot, then it means there's a connection. If there's no dot, then it's not a connection. The second one, input, is going to come from my B line here, and my third one is going to come from line C over here. The top one on the second gate is going to be connected to line A. The second one is going to be connected to line B. And I should probably get these lines out of here. And this one is connected to line C. And then down here, the top one goes to A, second one goes to B, and the third one goes to C. So I want the output to be 1 when this is true, or this is true, or this is true. So over here, we need an OR gate and set its number of inputs to 3. We're going to take this one and we're going to connect it. We're going to take this one, we're going to connect it. We're going to take the bottom one here and we're going to connect it down here. And then when we get done with that, we're going to put a red LED right there. So set your OR gate inputs to 3. Okay, you should be able to go up and click on your hand. And the times when you should get 1 are when your input is 3, 5, or 6. That's the number 3. That's the number 5. That's the number 6. Any other input, you should get 0 for an answer. Okay? So when you get all that done, go click on the hand, and that'll activate the circuit. And then start counting from 0 up to 7 on your 3 inputs. And when you get to 3, 0, 1, 1, you should get 1 for an output. When you get to 5, 1, 0, 1, you should get an output of 1. And when you get to 6, you should get an output of 1. Okay. You see a line there that's not green? That's a problem. This should be a little bit up there. Okay. And this also should be 3 inputs. Okay, now try them. Let's try all 8 of them. Does it work? Let's try all 8. Does it work? You should get a red light 3 times on 3 and 5 and 6. All working? All working? Got it? Working? 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 Okay. This isn't all that hard, is it? Okay. We are going to have digital functions that have ands and ors and nots all mixed up. And the rule is the first priority is going to be not. Okay. Well, actually, the first priority, I'll call it 0. Anything in parentheses. Okay. This is exactly like it is in math. Second is ands get done first. And the third one is ors get done last. And if you've noticed, the symbol for an and like the symbol for addition. And the priorities are the same. So, if I have something like A complement, B, C, now we got a complement on the outside. Actually, let's change that a little bit. Okay. If I get something like that, complement it when I get done. Okay. Okay, we're not going to build these. We're going to do some of this algebraically as well. But I want you to look at a little function here. And our function of A, B, C, and D is parentheses AB plus B complement C complemented. And I'm going to take that whole quantity and I'm going to AND it with D. And then I'm going to OR that with A, B, or CD complement, and then I take the complement of that, okay? And I'm going to tell you that A equals 1, B equals 1, C equals 0, and D equals 1. And if you want to figure out what that's going to be, if that's my function, you can just start substituting. But I basically got one big term here being ORed with another big term over here, right? So if I AND A and B together, what do I get? The answer is either 0 or 1. A is 1, B is 1. So with this specific set of inputs, if I AND them together, I get 1. Okay, now, I'm ORing that with this thing over here. Does it matter what this thing over here is? No, because I'm ORing it with 1. If this ends up being 0 and I OR 0 with a 1, I get a 1. If it ends up being 1 and I OR 1 with a 1, I get a 1. So I don't even need to do this, okay? Doesn't matter what D is. It does matter what D is because I'm going to AND that with a 1. If D is 0 and I AND it with a 1, I get a 0. If D is 1 and I AND it with a 1, I get a 1. So D is 1 though. So I'm going to, take this whole thing here. I don't care what this is. This is a 1. So I know the whole thing's going to be 1. I AND it with a 1, and that's going to be 1. Okay? Now I'm going to OR that whole thing with what's over here. Doesn't matter what's over here, does it? Because I've got a 1 on this side. Doesn't matter what I OR a 1 with. If it's a 1, I get a 1. If it's a 0, I get a 1. So I don't even, don't need to do about 3/4 of the work there. I can figure it out pretty quickly. Let's try another one. So this function is AC. You probably don't need to write these down. I'll put the notes up after class anyway. Plus BC D complement complement. They say BCD. Or complement B or BC. I think that's what I got. Yeah. Okay. So let's say I got 1, 1, 0, 0. And so I've got 3 things that are being ORed together. If I can find that one of them is 1, I can stop. Okay, so A ANDed with C, that's a 1 ANDed with a 0, that's going to be a 0. So I can't stop yet. B is 1, C is 0. Doesn't matter what D is now, right? Because if I got a 0 in an AND, it basically says the whole thing's going to be 0. So I know this is going to be a 0, and I complement a 0, I get a 1. So this is going to be a 1. So I'm ORing a 0 with a 1, and I'm ORing that with something else. Don't care what the something else is. I already know the whole thing's going to be 1 because I've got a 1 in the middle of a bunch of ORs. Okay? Same thing with AND. As soon as you find a 0 in an AND, you know that the whole thing's going to be 0. Okay. So we can simplify some of these digital functions algebraically. And this stuff is pretty simple. These rules are in the book too. You don't need to write them down. But we have an AND version of each one of these, and we have an OR version of each one of these. And the first one is, so A can be anything here, okay? A can be anything. And if I AND 1 with anything, what do I get? What's that? What if A is 1? Then you get a 1, right? What if A is 0? You get a 0. So what do you get? Maybe A, right? If A is 0, I get a 0. If A is 1, I get a 1. So this is kind of like multiplication. If you multiply something by 1, you get what you start out with, okay? There's an OR version of that. If I OR something with 1, what do you always get? Actually, I did the wrong one. I'm on the next row. It's not 1 with the OR. If I do a 0 with something, what do you get? The something, whatever the something is, okay? It's going to be A. So if A is 0, 0 ORed with 0 is 0. If A is 1, 0 ORed with 1 is 1, so I'm always going to get A, okay? Okay, the next one is if I AND anything with 0, what do you get? You always get a 0. Okay. If I OR anything with 1, what are you always going to get? 1. Okay. So it doesn't matter what this is. That's what we're just doing a minute ago. It doesn't matter what this is. If you got a 1, you can drop it. You can simplify. And here, it doesn't matter what A is. If you're ANDing it with a 0, you're going to get a 0. This could be some really complicated expression. So the A's here are not just single variables. They could be something really complicated, and it all still works. Now, how about this one? If I AND something with itself, what do I get? If you AND 0 with 0, what do you get? If you AND 1 with 1, what do you get? So if you OR something with itself, you get itself. Yeah, you OR 2 zeros together, you get a 0. You OR 2 ones together, you get a 1. How about this? If I take something and I AND it with its complement, what am I always going to get? What am I going to get? Pardon me? I can't get you through the mask. Josie, what are you going to get? 0. Because this is going to be 1, then this is 0. If this is 0, it's 1. There's always going to be a 0 in there somewhere, so you're always going to get 0 for an answer. There's an equivalent version over here. If I OR something with its complement, what do you always get? You're always going to get a 1. It's either going to be a 1 and a 0 or a 0 and a 1, but you OR them together, you're always going to get a 1 for an answer. There is, this one's hardly worth writing down. That simply says the order doesn't matter. Same thing over here, A ORed with B is equal to B ORed with A, and that's, remember that one from algebra? That's commutative property. There's also an associative property which says if you've got A and B, you AND them with C, it's the same as if you took A and ANDed it with B and C, and these two are really obvious. Same thing here, if I OR A and B together and then I OR the result with C, it's the same as if I OR the B and C together first and then OR the answer with A. Okay. Now we get to, there's 3 more, and these last 3 are more interesting than the first ones. So there's an AND version of this. If I take A and I AND it with B or C, this happens to work exactly the same way as it does in algebra. Remember what that's called in algebra? No? Well, but there's a name for doing that. What's the name for that? What property is this called? What's that? No, that's what I want. What'd you say? It's a distributive property. And actually, they always just call it the distributive property, but the technical name for it, you know what the technical name for it is? The complete name for it? It's called the distributive property of multiplication over addition. That ring a bell? So we're taking the multiply and we're doing it to this, and then we're doing it to this both. Okay? So that's the over addition part. So that's going to be AB plus AC. That is exactly the same rule that you learned in high school algebra. And then we get to the OR version of it. You know, there was no distributive property of addition over multiplication, was there? It was multiplication over addition. But guess what? If all you're dealing with is zeros and ones, this is kind of weird, I think, to kind of get your head around because it's so different from regular numbers. But you can distribute the plus over this. So I can say this is equal to A plus B ANDed with A plus C. That makes no sense. But if you were to sit down and create a truth table with A, B, and C, go through all 8 possible combinations of zeros and ones, work this out, and write down your column of zeros and ones. Make another column where you work this out and write down your zeros and ones. If there was a 0 on this row, there'd be a 0 on the same row over here. If there's a 1 here, there'd be a 1 over here. So those are the same functions. If the same inputs always give you ones and zeros the same, then the functions are equivalent functions. Okay? I'm not going to take the time to do a whole truth table with 8 rows and 2 more columns, but if you want to convince yourself, if you don't want to take my word for it, feel free to try it. Okay. Okay, here's an interesting one. A ANDed with A or B. Now, if you use a distributive property, you can help figure, it's easier to figure this out, I think. So if you do AA or AB. What if A is 1? Forget about B for a minute. What if A is 1? What's this then inside the OR? It's a 1. If I add a 1 with a 1, I get a 1. What if A is 0? Then in here I get B, but I end it with a 0. What do you get? So you're always going to get A. That's kind of a nice, that simplifies quite a bit. Just basically get rid of that part right there. And there is an OR version, A ORed with AB. If A is 1, doesn't matter what this is, the answer is going to be 1. If A is 0, that's a 0, but then I end a 0 with a 0, I'm going to get a 0. So that is always going to be, what did I say, A? If A is 1, I get a 1. If A is 0, I get a 0. Okay, and then there's one more. This is actually what we did in class the other day. AB complement. If you want to take the opposite of 2 things that are ANDed together, you take the opposite of the first one, you take the opposite of the second one, and you change the AND to an OR. So you take the opposite of each operator, each operand, and the opposite of the operator, and this is going to be A complement, that's the opposite of A, OR is the opposite of and B complement. And that one's probably not obvious by looking at it either. That one you'd probably have to build a truth table or build a circuit. And there's an OR version. If I have 2 things that are ORed together, and I complement them, that works the same way. So I take the complement of A, which is A complement, take the opposite of OR, which is and I take the opposite of B, which is B complement. Okay. All of these laws have names, and this is going to be an identity because if you multiply by 1 or add 0, you're going to end up with what you start out with. This is called, I think this one's called the null law. And actually I have to go back and look it up. I've only got a few papers here, and I may seem to have lost that. Oh, there it is. Okay, so yeah, this one's kind of weird. This one's called. I don't even know how to pronounce this because I've never heard anybody say it. I've only seen it written down. And depending on where you accent the syllable, there's probably a bunch of different ways to pronounce that. I'm not even going to try. This is called the inverse law. This is commutative, which you should already know. This is the associative, which you should already know. When I say this is the identity. This is null. And we've got distributive. And we've got, what's that one called? Absorption. Yeah, that's called the absorption law. And this one is called De Morgan's law, after a mathematician who must have been the first one to figure that out. So part of your homework, we're going to do some circuits for homework, but I've also got some function simplification for you to do for homework. And we'll do one problem here. And actually, you know what? We'll do the first homework problem for you. All I got to do is find it. I don't think I brought a hard copy with me. Go look at the homework down at the bottom of the page, and click on Boolean algebra number 1, and tell me, open that Word document up and tell me what number 1 is. ABC plus and it says to reduce that to what? A single variable? Okay, so it's either going to be A or B or C, or A complement or B complement or C complement when I get done. So this can be simplified a lot doing Boolean algebra. Now, the thing that I end up doing most often when I'm trying to simplify this stuff is I look for something and its complement multiplied by the same thing, okay? So I've got A and A complement both multiplied by BC. And if you look at the other ones, I've got A and A complement multiplied by B, C complement, okay? So I'm going to take these two, get A, B, C, ORed with A complement B, C, and then I'm going to move this one over here. It's going to be A complement B, C complement, ORed with A, B, C complement, okay? So I pull the BC out. So this is the distributive property in reverse. So I pull the BC out, and what's left here is I can multiply that by A, or I can multiply it by A complement, okay? This is exactly like you do in high school algebra. And then over here, I pull the BC complement out, and what I'm left with is A complement or A. And you want to look for these a lot because you know that anything ORed with its complement is always 1. Okay. So this is going to be BC ANDed with 1. And over here, this is going to be BC complement ANDed with 1. Okay. And then this is just obviously BC ORed with BC complement. Okay. Well, I can factor a B out of that. So if I factor the b out, I've got c ORed with c complement. And you know what that is, that's 1. So I've got b ANDed with 1, which is just plain old b. So it said reduce it to one variable, and that's the, instead of having this big old mess up here on the top, you could replace that whole thing just with plain old b. Okay. So as you do this, the other thing I want you to do is I want you to tell me how you were able to do this. So this is just, we'll just say commutative here because all you're doing is rearranging the terms. When you go from here to here, that's that idempotent or whatever you pronounce. I'm just going to put IDEM over here for that property to get from here to here. And to get from here to here, that's the identity property. And to get from there to there, that's just factoring. That's my distributive property. Oh, I was off by one. I did the rearranging up here. And then down here, I did the distributive property. Okay. And then down here, this is just idempotent. And this one is to get from here to here, I apply the identity. And that's it. So I've got a handful of those for you to do. And every time you do one, you know, when you go from this step to this step, just to go to the side and say what law you applied to make it work. Most of them are relatively straightforward. The first thing you're almost always going to do is you're going to apply this distributive property here by looking for something that you can factor out of at least 2 of the terms. Maybe you can factor it out of 3 or 4 of the terms, okay? But look for a common term that you can factor out, or in this case, it's actually 2 terms that I'm factoring out. And then what you want to be left with is something ORed with its opposite. And as soon as you get something ORed with its opposite, you know that you can replace that with a 1. So it just drops out. And you know what? That's probably a good place to take a break. Let's take about a 7-minute break here. That would be starting about, what time does your computer say? Your phone? What's that? 1:30, 34? Start up again at 1:40, okay. How good are we going to be?
Another question.
Where'd you guys end up last year? It wasn't a good year, was it?
No, we were right around 500.
Yeah.
I think we were 1 game above.
But didn't you lose a ton of close games?
Yeah, like 2 or 3 points.
Yeah. You don't need to copy this down. So what'd you do before class, before there were cell phones? So this is a major step forward then, huh? Time's your cell phone say? 40? It's time to go then. Okay, put your cell phones away. So let's take a look at some more digital functions. We're gonna look at some other ways to kind of simplify things here. So these, I've got 3 input functions, so there's 8 possible combinations of 3 things, 3 bits. And so I've got 8 rows here, numbered from 0 through 7. And it looks like I'm gonna get one here, and here, and here, and here. So what I'm saying here is I'm gonna get, you can just get this right off the truth table, I'm gonna get a 1 when A is 0, so you complement that, and B is 1, and C is 0, so C has to be complemented before it goes through the gate as well. Here it's when A is 0, and B is 1, and C is 1. Or I can get a 1 when A is 1, and B and C are 0. Or I can get a 1 when all 3 of them are equal to 1. Okay? So you can read it right off the truth table. Just look at the rows where the 1s are, and that's going to be what your function is. Okay? Now, you may or may not be able to simplify this. You know, you would have to look at it and see if you can factor it or anything. But these terms right here, there's a special name for them in, you know, digital circuitry, and these are called min terms. I don't know if the min is, you know, like short for minimum, or I don't really know where it comes from, but a min term is a term that has all of the inputs in it. So if I had something like AB, you know, or I had B, C complement, those are not min terms because they don't have all 3 of the inputs in them. So I've got all three here, all three here, all three here, and all three here. And by the time I get done simplifying it, they will probably not be A, B, and C in every single one of the terms, okay? So you could easily create that. As a matter of fact, let's build that, okay? So let's go, and actually you've got one with 3 inputs, right? Why don't you just leave the 3 inputs there on the left and drag your mouse over everything on the right and hit delete to get rid of those. I don't know if you've noticed or not, but in order to delete something on the screen, you have to get the mouse around every single bit of it. If you get your mouse around 90% of it and leave a little bit of it unselected, it will remain on the screen. So make sure you get the mouse around everything that you want. So we're going to have A here, we're going to have B going down here, we're going to have C going down here, okay? And my first gate is going to be complementing A and complementing C. So I should have said to leave these. Did you leave these? So we're going to complement A and we're going to complement C. So we need an inverter here, we need an inverter here. And then this goes to A, this goes to B, this goes to C. And then a 0, 1, 1. So on the next one, this needs to be inverted and the other two do not. This is A, this is B, this is C. And then 1, 0, 0. And the last one is 1, 1, 1, so I don't have to invert anything, I just connect everything. And then we run all of those through a 4-input OR gate. And then that to an LED output. 2, 3, 4, and 7. So when our input is 2, 3, 4, or 7, we should get 1 for an output. It's probably easier to draw these on the board than it is to draw them in Logisim, isn't it? Does it work? Yep, all you gotta do is connect them in the right order now and you're good. Can't go all the way through. You can't go all the way through. Just do Control Z. Okay. You can do a Control Z to undo. Okay, change the inputs, yeah. You know, you had two lines that are disconnected, right? Test it?
Yeah.
It works? Good. You ever see a red line or a blue line while you're doing this stuff? You know you got something wrong. You got to have probably just delete the red line or the blue line and start over again. Test on all 8 possibilities. Let's test it. Works? Okay. When you're testing these, it's not enough to test it on the places where we get 1 for an output. You also got to test it on the places where you get 0 for an output. Otherwise, you don't know for sure if it's working. Pardon me? Why is it all red? Well, that's a good question. When did it turn red? When you turned it on?
We're just gonna move this.
Okay. Well, those all appear to be connected. Right here, right here. You get this connected to 2 inputs, or to 3 inputs. Okay, so delete that, delete that, delete that, and we'll just drag this over now. And those little things don't matter. Now let's see what happens. There you go. If you have one input line connected with another line, you're going to get red. So if I, you know, in the course of crossing this vertical line right here, if I did that, then I got B and C both inputting to the same gate, and that's not going to work. Okay. Okay, so everybody's got it working or pretty close to having it working. Now, this is called a product. I'm sorry, I just said it backwards. This is a sum of products. And, you know, we keep getting this, the notation looks like multiplication and addition, and the terminology is like multiplication and addition as well. So here's a product, a bunch of ands, here's a product, here's a product, here's a product, and I'm summing them or oring them together, okay? I mean, another way to say it would be it's an or of ands, but this probably sounds a little better, okay? So that's a sum of products. There is also, you can turn that around and you can have a product of sums. Okay, so product of sums is where you got some things that are added together and some other things that are added together or ORed together if you want. And we AND all of those. Okay. And we're going to look at a way to turn this from a sum of products into a product of sums. If we turn it into a product of sums, it actually turns out to be easier, cheaper to build. Okay. So this part's a little tricky, but it's just basic algebra. So don't get distracted by your phone or something while we're going over this part. Okay. So these are called min terms, and we're going to name them M0, M1, M2, M3, M4, M5, M6, and M7, okay? And that's just a notational thing, so I don't have to write A, B, C, I'm sorry, A complement, B complement, C complement, A complement, B complement, and so I can write less, but it's just another way of saying the same thing. Okay, so if you define a function by the places where it's 1, then this function is equal to M2 or M3 or M4 or M7, right? M2, M3, M4, M7. So if M2 is 1, or M3 is 1, or M4 is 1, or M7 is 1, then that's my function, okay? Now, what's the opposite of that function? The opposite of that function would be if you get a 1 here, and a 1 here, and a 0, and a 0, and a 0, and a 1, and a 1, and a 0, okay? Every place where there's a 1 in this function, you get a 0 in the opposite. Every place where there's a 0, you get a 1 in the opposite. So the opposite function here would be, so we're going to call it the complement, would be M0 or M1 or M5 or M6. Okay. Now, what if I take the complement of the complement? What do you end up with? The original. You're right back where you started, okay? So I'm going to take the complement of the complement, okay? So, well, the complement of this is M0 or M1 or M5 or M6, okay? And by the way, this is in the notes too, so if you don't need to write it down, you just, I'd rather have you focus on this up here. So that, whoops, opposite, okay? So now we can do the De Morgan's law thing. If you want to take the opposite of a bunch of things that are ORed together, you take the opposite of each individual one and you AND them together. So it's going to be M0 complement ANDed with M1 complement ANDed with M5 complement ANDed with M6 complement, okay? I'm really just doing algebra so far, okay? So that is F complement complement, which is equal to the original function, and that's what I get. Now, what is the complement? Now we're going to go back and we're going to substitute this. What's the complement of M0? Well, M0 is, actually, let's just substitute in here. I'm running out of room down here. So this is going to be F equals A, B, whoops, that's 0, right? So all the terms are 0, and I want to complement that. Or, whoops, not or, I'm ANDing these together. And I'm doing M1, and that's going to be A complement B complement C. Take the opposite of that. And then I'm going to do M5, and that's going to be A B complement C. I'm going to take the opposite of that. And then M6, and that's going to be A B C complement. Okay? It's starting to get kind of ugly, but there's only one more step left. So what is the opposite of things that are ANDed together? You OR the opposites of what's inside the parentheses. So I'm going to take the opposite of A complement, which is A. I'm going to OR it with the opposite of B complement, which is B. I'm going to OR that with the opposite of C complement, which is C. Okay? Now, this one is going to be the opposite of A complement is A, ORed with the opposite of B complement, which is B, ORed with the opposite of C, which is C complement. This is A complement ORed with the opposite of B complement, which is B, ORed with the opposite of C, which is C complement. And the last one is the opposite of A, which is A complement, ORed with the opposite of B, which is B complement, ORed with the opposite of C complement, which is C. Okay, and we're done. What is this? This is a sum and a sum and a sum and a sum, and it's a product of sums. Okay. Now, this term we get from here. This term we get from here. This term we get from here. And this term we get from here. So do you see a connection between what I've got there and the zeros and ones that are over here? If there's a 0 here, it's uncomplemented over here. So 0 for A, 0 for B, 0 for C, so it's A, B, C. Now, that should be a 0, that should be a 0, but that should be a 1, and 0, 0, 1, okay? So you just kind of turn everything around here. This is a 1 and a 0 and a 1, and so that refers to the row where 1, 0, 1, and the last one is 1, 1, 0 if I flip them all, and that's row 1, 1, 0, okay? So there's two ways, now that you know this, there's two ways to get the function from looking at the truth table. The simple one is the sum of products, which you just look at the rows that have 1s in them. But you can also look at the rows that have 0s in them, and it's a little trickier. You got to remember a little more to do it. But wherever there's a 0, you use the uncomplemented term. You OR it with, you know, the next term. If it's a 0, it's uncomplemented. If the next one's a 0, it's uncomplemented. So A or B or C. So you kind of look at the rows where the 0s are and put pluses in between them. Turn all the 0s to 1s and all the 1s to 0s, and you've got it. Okay? If you have a hard time remembering that, write it down. But that's how you can easily get a product of sums instead of a sum of products. Okay. Okay, let me give you one. You try to do this on your own. Made kind of a mess up here, but we'll see if we can get it back. So here's my function. My function is 0, 1, 1, 0, 1, 1, 0, 1. Okay? So I want you to do two things. The easy one is the sum of products. So write out the sum of products. There's 5 1s there, so there should be 5 terms in your answer. And after you've done that, then look at the 0 rows and come up with a product of sums for me. And let me know when you get each one, and I'll take a look. Pardon me?
Which one?
First, do a sum of products. So that's where you look at the rows that have 1s. Okay, that's the easy one. That one reads easily right off of the table. We got a sum of products for me to look at. No, you're doing it backwards. You want to look at the 1 rows and A complement, B complement, C.
Am I right in assuming that
Is that a complement there? ABC complement? No, you're doing it backwards.
Okay.
I think I messed some of you up by showing you that second way. The first way is exactly the same. Just look for the rows that have ones. If there's a 0 there, it's complemented. If there's a 1 there, it's not. All done? So A complement, B complement, C, A complement, B, C, A, B complement, C complement, A, B complement, C, A, B, C. And then this one would be here B or C, A or B complement or C complement, and A complement or B complement. Yep. Piece of cake, isn't it? Who else is done? Oh, you're doing, okay, let me see. Okay, so this should be 0, 0, 1, complement, complement. Where's the complement, complement, and a 1? No. So that's A complement, and so when A is 0. Okay, okay. And then 0, 1, 0, and then 1, 0, 0, and then 1, 0, 1, and then, yeah, okay. Yeah, you just threw me off on that one. But the rest, yeah, the rest of them are good. Now try the other one where you look at the 0 rows, and that's where you're going to get a product of sums, and that's where you have to flip the values of the zeros and the ones. Yes. And if you substituted, then that would just be A complement, B complement, C, A complement, B, C complement, and yeah. And then the other one with the, do you have the other one done? Should be the rows with zeros on them. So there should only be 3 terms here, and you got 4. So it's just the rows with zeros. So it's this row and this. You got, that's supposed to be, let me see, 0, 1. Oh, you're still doing the old function, I think. I changed the function up there to 0, 0, 1, 1, 0. Tamish, you got it? Complement B complements. Okay. So 0, 0, 1, 0, 1, 0, that's a 2, 0, 1, 1, that's a 3. No, it's not 3. And this is, these two are the same. You got, aren't they?
Yeah.
So you don't need it in there twice. No, you're still complimenting too many things. Let's, the sum of products, you just look at the rows where the ones are, okay? So what you're saying here is, I'm gonna get a 1 if A is 0, and B is 0, and C is 1. So that means if A has to be complemented, and then B has to be complemented, but C does not have to be complemented before it goes through the AND gate. If I do that, if this is 0 and I complement it, and this is 0 and I complement it, and this is 1, I leave it alone, I'll get a 1 for an output when I add all 3 of those together, okay? Then on the next one, it's where I've got a 0 and a 1 and a 0. So A has to be complemented, B does not, C has to be complemented. The next one is row 4, so I've got 1. Well, these are from last time, aren't they? So I've got 1, 0, 0. So A is not complemented, but B is and C is. And then C is the only one that's complemented, so it's going to be A, C complement B, and then the last one is they're all 1, so it's got to be A, B, C. Okay, so that one's easy. You shouldn't have any trouble doing that one, but I think I got some of you messed up by showing you the other version. So that's one way to do it. But the other way to do it is look at the 0 rows. Look at this row and this row and this row. And the rule is change the zeros to ones and put pluses in between. Okay, so this is going to be A or B or C. This row is going to be A or B complement or C complement. And this row down here is going to be A complement or B complement or C. Okay.
So they're both right answers, then the top one is?
They are the exact same function. If you sat down and you did A, B, and C for inputs, and on the top you had 5 AND gates and a few inverters, and on the bottom you had 3 OR gates, and then they ran into an AND gate, and then you ran through all possible combinations. Whenever you got a 0 up here, you should get a 0 down here. If you get a 1 up here, you should get a 1 down here. Okay?
So if, for example, you asked us a question on like the test or an exam, you said give me the sum of products, it would be the top one, right?
That's the sum of products.
That would be the only thing we'd have to put, right?
That'd be the only thing you'd have to put. And the next question on the test will be,
Product of sums.
give me a product of sums. Yeah. I can guarantee you. Okay. Okay. Go to your file menu in Logisim, and we're going to create a new circuit. And we're going to do, well, we'll look at this a couple of ways. We got A and B, 2 inputs. There's 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Okay. And the function is 1, 0, 0, 1. You might remember that from the other day. That function tells you when the inputs are equal. If I get 2 zeros for input, I get a 1 for an output. If I get 2 ones for input, I get a 1 for an output. So it's testing for equality of inputs. So that's my function. To write that algebraically would be A complement, B complement, or A, B. So that's my function. The function is 1 when A and B are 0. It's also 1 when A and B are 1. If I want to do it the other way around and do my product of sums, then I look at the 2 0 rows here, and I just invert things and put a plus sign in between. So the 0 is going to become an A, and the 1 is going to become a B complement. And this is going to be A complement ORed with B, okay? So 2 versions of the exact same function. Okay, now you got Logisim open. Let's put 2 inputs up here. After you got them, make them face south and label this one A, label this one B. So build that circuit, set the inputs to both 0. You should get a 1 for an output, and then count up to 3. When you get to 1, it should be a 0 for an output. When you get to 2, it should be a 0 for an output. When you get to 3, it should be a 1 for an output. If you get any red lines there somewhere along the way, I would just do an undo. Control Z. That's pretty sneaky. I always do 3-line segments, which means I have to lift the mouse up once and start again. But if you only got 2, you can sneak them in that way. Okay, you should be able to run it now if the inputs are both 0. So click on the hand. Yeah, click on the hand first. Now, okay, now if you turn 1, it should go off. Turn that back to 0, go to 2. Now turn them both on. There you go. It's working. Working? Test it. Testing it right now. So you get 1 only when the inputs are equal. Okay. Okay, now click on your finger, try all 4 possible combinations. Okay. Now what we want to do is we want to build this circuit using only NAND gates, okay? There's not a single NAND gate up there. Why we want to build it with NAND gates? Actually, NAND gates require less circuitry to build than AND gates do, which seems kind of funny because you got that inverter on the end, so it seems like it would take more, but it does not. I want to make this just out of NANDs. So what I can do, I can make these into a NAND just by putting an inverter on the end, okay? And rather than replacing that with an AND, why don't you just put an inverter on the end here instead? So it looks like this coming out. I think that's less hassle than replacing the gates. Okay. So basically that's an AND. I mean, we drew it as an AND with an inverter on the end, but basically it's an AND. But it's not same function anymore because I turned these 2 around. But what if I do this? What if before they get to the OR gate here, now don't do this, just watch what I'm doing on the board, okay? So what if before I get to the OR gate, now I'm right back where I started, right? I haven't changed the function at all. So if there's a 1 coming out here, it goes to a 0 and then it gets back to a 1. If there's a 0 coming out, it goes to a 1 and then back to a 0. So if I put 2 inverters on a line, it doesn't change anything. And that's what I've done. So what was my goal here? My goal was to create something out of NAND gates and only NAND gates. Well, I'm 2/3 of the way there because those are now NAND gates. But I want to make this into a NAND gate as well, okay? Now, let's pretend that the signals coming in here are called X and Y, okay? Then what's coming out here? It is X complement ORed with Y complement, right? And according to De Morgan's law, this is the same as X, Y complemented. Okay, what's this? That's an AND. I complement an AND, what have I got? I've got an AND. So this part can be replaced by a NAND gate. Okay, so That's why I didn't have you put those inverters in there. So get rid of the OR gate, put a NAND gate in here. And now, if we assume these are NAND gates, which functionally they are, we've got nothing but NAND gates making up doing this function, okay? And you should be able to do that again. If you do 2 zeros for input, you should get a 1 for an output. If you do 2 1s for an input, you should get a 1 for an output. And anything else, you should get 0 for an output. But what we started out with was an AND here, an AND here, and an OR here. So if you can come up with this version of the function, changing it to NANDs is a piece of cake. All you do is you replace this with an AND, you replace this with an AND, and you replace this with an AND. So you take everything that's there, make it into an AND. And you're good. Okay, start a new function, a clean breadboard in Logisim. Actually, you know what? Why don't you copy, go here and copy. You drag the mouse around A and B, and the lines come. You got to get all the way down to the bottom of the lines, or they won't come with you. You got to get the whole thing inside the box, and do Control C, and then just paste that in on the new one. So we're not completely starting from scratch. So we've got this, and we've got this, and now we're going to implement this version of it, okay? And again, this circuit tells us if the inputs are equal. So if we got 2 zeros, we get a 1 for an output. If we got 2 1s, we get a 1 for an output. Otherwise, we get a 0 for an output. So this is going to be an OR gate where I complement B. So let's put an OR gate here with 2 inputs. And B gets complemented. A goes straight in. We'll put another OR gate down here. And on this one, A gets complemented. And B goes straight in. When you get it built, try all possible combinations of inputs. Try all 4 combinations. You should only get an output when the inputs are both 0 or both 1. It works. You better do Control Z. You're connected to both lines now, I think. There you go. Yeah, good. Working, Leo? Josie, working? Ben? Demas? Okay. Now, guess what we're going to do with this one? We're going to turn it all into NORs. And you can probably guess what I'm going to do here. I am going to make these into NORs by just putting an inverter here. And then I've got an AND gate over here, and I'm going to invert before I get there. Now let's say that this line right here is X and this line right here is Y. What's this? This is X complement ANDed with Y complement. And what is that? That is X or Y complemented. And I've got an OR that's being complemented, and we call that a NOR. So what you want to do here is replace that with a NOR. You'd also replace these with NORs if you wanted to, and then test it with all 4 possible combinations of inputs. You should only get an output of 1 if the inputs are both 0 or if the inputs are both 1. So if you have a sum of products here and you want to do it with NANDs, you just basically just do it and then replace everything with an AND. And if you've got a product of sums, you just design it and basically replace everything with a NOR. It's that straightforward. Okay. So you can simplify these functions by doing Boolean algebra. There's another way to simplify them though, as long as they're not too complicated, which means as long as there's not more than 4 variables. If I have A, B, and there's 0, 0, 0, 1, 1, 0, 1, 1, this is the term that corresponds to A complement, B complement. This is A complement B. This is A, B complement, and this is A, B, okay? And what I'm going to do is I'm going to take that truth table, I'm going to rewrite it. I'm going to put A over here on the left. A can be 0 or 1. And I'm going to put B up here on the top. B can be 0 or 1. And this corresponds to A complement, B complement. This corresponds to A, B complement. This corresponds to A complement B. And this corresponds to AB, okay? It's exactly what I had over here. I just made it into a 2x2 box, 1x4 column, okay? But by doing that, I just did something kind of neat. Let's say that I have a digital function, and that's my digital function, okay? Now, you know that you can simplify that by pulling out A complement. This is 1, which is just A, okay? I'm sorry. I didn't bring my complement down. So that's A complement. So you can factor that. You can do it with algebra and figure out a simpler way to write it. But this term is right here, and this term is right here. They're both in the same row. And what do you know about this row? That is the row where A is 0. That is the A complement row. It doesn't, B's not affecting that at all. If B is 0, I still get A complement. If B is 1, I still get A complement. Okay? So this row is the row where A is 0, and that's all you really need to know. What's this row down here? That's the row where A is 1. What's this column right here? It's the column where B is 0, right? Over here, this is the column where B is 1, okay? So this is what we're doing here is if you find two cells in a row like this, well, just look over the side and see what variable that is. That's the A complement row. If you see these two down here, you look over the side and well, that's the row where A is 1. So that's the A row. And you can just write down A instead of these two terms here. Basically what we're doing is we're kind of drawing a picture of how the factoring works. You know, if you just have these two cells right here, then that's just where B is 0. Doesn't matter what A is, just B is 0. And if I have these two cells right here, then that's where B is 1. Okay. Now here's let's try this one. Let's take what I had originally up here. I'm going to add on one more term, AB. Okay. Now, if you factor that, you're going to factor this first probably, and you'll get A complement, B complement, or B, and we'll just leave this over here plus AB. And if we go down here, we know that that's 1, so it's going to be A complement and with 1, or AB, and it's going to be A complement or AB, and that's what we end up with. Okay. Now, if I start off, if these are my terms, A complement, B, that's this right here. And this one is this one right here. And I can draw a rectangle around those. It corresponds to where A is 0. And I'll get A complement. Okay. Now, I can also take these two terms and I can draw a box around those, and that's where B is 1. Okay. So it's A, whenever A is 0 or B is 1, my function is going to be 1. And check this out. This and this are the same, but this one's simpler. So what you're doing here when you do this visual factoring is you are looking for rectangles in the box here that are 1 by 2. As a matter of fact, that's the only kind of rectangle you can have there unless you had all 4 of them, in which case the function would just be 1. Okay. But you can extend this to 3 variables. Okay. With 3 variables, we're going to do A and B across the top. So A and B across the top, and we do C over on the side. So with 3 variables, there's 8 possible combinations of zeros and ones, so you need 8 boxes here. And this is when A is 0 and B is 0. A is 0 and B is 1. And normally you count to 2, but we're going to do A is 1 and B is 1, and A is 1 and B is 0. And over here, for C, we're going to do 0 and we're going to do 1. Okay? I'm not going to write all the terms in here. This would be A complement, B complement, C complement, A complement, B, C complement, and so on. And this row is the C complement row, right? That's where C is 0. And if I've got this term plus this term plus this term plus, maybe I should write them in. So if I've got A complement, B complement, C complement, or A complement, B, C complement, or A, B, C complement, or A, B complement, C complement, if I've got all of those filled in, then the A's and the B's aren't doing anything at all. You could take your rules of algebra, you could take the stuff that's here, and you could factor it, and what you would end up with is C complement. Okay? We could do that, but if you don't believe me, try it on your own. We won't take the time to do it here. So if I had something down here, this is going to be where A is 0, B is 0, and C is 1. A is 0, B is 1, and C is 1. A is 1, B is 1, C is 1, A is 1, B is 0, and C is 1. Okay? This is the row where C is 1. It doesn't matter what A is, it doesn't matter what B is, because I've got all possible combinations of A and B here, along with C complement. They're not contributing anything. They're not contributing anything. All that matters there is that C is 0 up here, C is 1 down here. Okay, so what am I looking for now? I'm looking for a rectangle that is that big. And that's basically the same as taking the C complement out of there and factoring A complement, B complement, or A complement B, or A, B, or A, B complement. And this is all 4 possible combinations of A and B. So I'm saying it doesn't matter what A and B are, I'm going to get a 1 no matter what. So you could actually factor this more if you wanted to, but basically that's going to end up being a 1. And so I'm going to end up with C complement for this row. So I'm looking for every place where C is 0. So I'm looking for rectangles that I can draw on this, okay? This row down here is the row where C is 1. Now, there's other rectangles up here as well. Here's a rectangle. And what does that correspond to? What do all 4 of those cells have in common? A complement. A is 0, right? And if you look, there's 2 columns where A is 0, and it's these 2. So if I can select everything in this column, in these 2 columns, that's another way of saying A complement. So if these 2 are A complement, guess what these 2 are? Those 2 are A. Now, what about these 2 right here? B is 1. That is all the places where B is 1. So these 2 onto B. If I've got a 1 here and a 1 here and a 1 here and a 1 here, I can replace that with B. Now, these 2, if I've got all 1s in these 2 cells and all 1s in these 2 cells, those 2 cells are the place where B is 0. And that makes sense. If the 2 columns in the middle are where B is 1, then the 2 outside columns are going to be where B is 0. Okay? So what am I looking for now? I'm looking for rectangles again. And the only rule is that the sides of the rectangles have to be a power of 2. Okay? Have to be a power of 2. So I can't, so my powers of 2 are 1 and 2 and 4. I can't select something that has 3 in it. But I can do a 1 by 4. Those are both powers of 2, and that's for C and C complement. I can do a 2 by 2 and get that, or that, or that. And this other one's considered a 2 by 2 as well. Yeah, imagine picking this up and kind of wrapping it around if it's a piece of paper, so they're adjacent. These 2 are adjacent to one another. And so you can actually draw a rectangle around there. This is what your rectangle looks like. If you pulled it off the board and wrapped them around, you'd have a rectangle. Okay. You can also do just a 2 by 1 right here. What's this? I've got C complement, I've got C, but in both cases, A is 0 and B is 0. Look at the columns up here. This is the only place where A is 0 and B is 0. So this is my A complement, B complement column. If I got 1s in there, then it's A complement, B complement. If I've got 1s here, just in those 2, those are the 2 cells where it's the intersection of where C is 1 and where B is 1. So this would be BC. This is the only place where I've got where B is 1 and C is 1 both. Okay, so I can replace these 2 with the simpler BC. And if you look at it, it's A complement ANDed with BC, and it's A ANDed with BC, and you can factor the BC out, and the A ordered with A complement is 1, and it's just plain old BC. You cannot do a side with a length of 3. I can't factor that. I mean, I could factor these two, but I can't do all three of them at once. I have to get two terms out of that, not one. And guess what? There is also a 4-variable map. These are called Karnaugh maps, after the name of the guy who came up with them. And sometimes people just call them K-maps instead. And a 4-variable looks like this. Oh, it's going to be 4 by 4. And so this is going to be AB over here. AB can be 0, 0, 0, 1, 1, 1, or 1, 0. It's going to be 0, 0. It's going to be CD up here. And they can be 0, 0, 0, 1, 1, 1, or 1, 0. And if you're wondering why I'm counting 1, 0, 1, 3, 2 instead of 0, 1, 2, 3, the only way this works is if from this cell to the next one, there's a difference of 1 term. So from here to here, I'm changing this 0 to a 1. From here to here, I'm changing this 0 to a 1. From here to here, I'm changing this 1 to a 0. And from here back over to here, I'm changing that 1 back to a 0. Okay. If I put them in another order, I couldn't draw the rectangles the right way. So this is going to be 0, 0, 0, 0. I'm just going to do the numbers instead of the letters. This would be 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. This would be, these are my first two bits, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0. Down here, the first two are going to be 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0. And down here, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, and 1, 0, 1, 0. Okay. So you want to do some factoring now. You look for the biggest rectangles whose sides are a power of 2. Well, the biggest one here would be 4 by 4. If there's a 1 in every one of these cells, what's my function? Just 1. It's always 1 no matter what the inputs are. So it's just 1. The next smallest ones I could have a 2, 4. That correspond to. When A is 0. Yep. C and D, they're not affecting at all. I go through all possible combinations of C and D. If I'm going all the way across, I'm doing all the combinations of C and D, and they're not affecting at all. And B isn't making any difference either because I'm doing all combinations of A and B. So this is just A complement. So what do you suppose this is down here? That's got to be A then, right? That's where A is 1. Now, what about these two rows right here? Those are the two rows where B is 1. So that's B. And then, you know, for the other one, we got to kind of do this part up here and this part down here. And those two together are where B is 0. And then if we do the same thing with C and D, these two columns right here, that's where C is 0. So that's my C complement. And these two is where C is 1. So that's going to be my C column. And then the two in the middle here are where D is 1. And then the one out here and the one out here are where D is 0. Okay. So you're trying to simplify circuits now. What you do is you look for the biggest possible rectangles that you can draw, but you can't have sides of length 3. They have to be 1, 2, or 4. Okay. So let's try a couple of examples before we quit here. Okay, so let's say that we have So this is basically a truth table. I'm going to put in where the ones would be. Let's say I've got a 1 here, 1 here, 1 here, 1 here, and every place else is a 0. Okay, that's a 2 by 2 rectangle, right? I can draw a rectangle around that, and that corresponds to the 2 rows where B is 1, and it intersects with the 2 columns where C is 1. Okay, so that is BC, and I didn't have to do any algebraic factoring at all. All I had to do was look at the map. Okay. Now, what if I've got a 1, 1, 1 like that? Well, this is BC. This is still BC. I want to get these others in here, and what you can do is you can overlap. I can select that 1 here again to get the biggest possible rectangle. And now that is the 2 rows where A is 1, and it's the 2 columns where D is 1, AD. So even if it's already been used, you want to pick the biggest rectangle you can, and that'll give you a simpler term over here. Let's say that I have something like this. I've got all 1s here, and I've got 1s here. Okay. Well, here's the biggest rectangle I can draw on this row. That's all of them. That is where A is 1 and B is 1, and C and D don't matter. So it's going to be AB. And then if you can reuse them to make the rectangle that you draw a little bit bigger, then you do it. So this is where, what row is that? That's the row where A is, 2 rows where A is 1, intersecting with where D is 1. So that's going to be AD. So that's a simplified version of the function. So you can do Karnaugh maps with up to 4 variables. Have a homework. I've got several homework assignments for you. Unfortunately, if we're going to do this all in 4 weeks, then you're going to have more homework every night than you would otherwise. If you go to the bottom of our page, there are 2 Boolean algebra pages. I think one of them has 10 questions and one of them has 6 questions. And there are 2 labs to do as well. And I think the first lab is straightforward. The second lab is doing the first lab, but with nans and nors instead of ands and ors. Okay, so, and that's real straightforward too. I'll put the notes out there in about 10 minutes. So if there's anything we went over in class, back, look at it. And actually the stuff on Karnaugh is a little more detailed than what I went over in class, just because we didn't have enough time. So see you tomorrow. You'll hand in hard copies of the Boolean algebra. You'll hand in the drop box the 2 circuits.